Okay, and welcome to the first video in differentiation in Pure 1. Differentiation and integration are very important topics in the A-level course. You'll see them throughout the Pure material, and you'll be applying the methods that you'll see over the next few videos repeatedly. So it's very important that you understand the concepts. Let's just get into the worksheet and let's go through the theory behind differentiation. So what is differentiation all about? At GCSE, you looked at the gradients of lines, y equals mx plus c. Differentiation looks at the gradient of a curve. Okay, so the gradient of a curve is found from the gradient of a chord that joins two close points on the curve with coordinates x, fx, and x plus h, fx plus h. What does that mean? So imagine I've got a section of a curve and I make a chord between 2 points. Okay. One coordinate of that chord will be x and y, or fx, and the other coordinate will be some x value to the right, so plus h along, and therefore the y value will be fx plus h. Okay, so I'm just going to draw a little triangle here, okay, just to show what's going on. So there's a difference of h between these x values, okay, and this difference here in the y values is fx plus h minus f of x. Okay. Now, if I want to find the gradient of this chord, all I do is fx plus h minus fx, change in y, over the change in x, which is h. Okay, so the gradient would be fx plus h minus f of x over h. Okay. However, that would just be the gradient of the chord. What if I want the gradient of a point on that curve? If I want the gradient of a point on that curve, let's say I want the gradient here, okay? Then what I'd need to do is I'd need to reduce the length of that chord such that it gets closer and closer to that point. So imagine I'll move from there to there. You see that the chord is getting closer to the gradient of the curve. What if I move that point upwards a bit more? You can see it's getting closer and closer. So what we're trying to do here is we're trying to shift one point closer and closer to the point which we want to find the gradient of, and that theory will inform the differentiation from first principles formula, which is given here. Okay. As we move this point up and up towards x plus h, the value of h reduces. Can you see, look, the value of h is there. As I move my point up, it gets shorter. As I move it up, it gets even shorter. That value of h will become smaller and smaller and smaller. Essentially, it will tend to 0. And at the point at which h becomes 0, we found the gradient at the point. Okay? And in fact, at all points on the curve. And here's the formula here, which, as you can see, is literally a change in y over change of x, with this limit as h tends to 0, which we need to include in our working. So in year 12, we need to think about that in terms of our theory, using that formula, and that will help us to show the derivative, or in other words, gradient at a point on a curve. Okay, so whenever you see the word derivative or dy dx, that means gradient at a point, any point on the curve, or a particular point on the curve. Okay, so let's look at part A. We might also need to use these binomial expansions. Let's look at part A, y equals 4x minus 3. We've got to show that the gradient at any point on that curve, or dy dx, the derivative is equal to 4, using differentiation from first principles. So I'm just going to show it just by using a bit of theory. So 4x minus 3, that's a straight line. Now let's pick an x value, x, and the y value. Now remember, the y value we normally write as f of x, which in this case will be 4x minus 3. Yeah, the y value would normally be 4x minus 3. And I've got a point along, which is x plus h along, and the y value for that will be 4x plus h minus 3. Okay, I think we should understand that, yeah? X plus h is the x value, therefore the y value will be 4 brackets x plus h minus 3. Therefore, when I do differentiation for first principles, if I think about the value of the gradient, now this is a straight line, okay, so I can literally just look at it like that. The gradient dy dx will be equal to the limit as h tends to infinity, h tends to 0, this gap here between the x values, that's h, of the change in y, fx plus h minus f of x over h. So fx plus h will be 4x plus h minus 3, okay, over f of x. Sorry, over h minus 4x minus 3. Okay, so I repeat that again. What I've done is I've found the y value, y2, minus y1. y2 is 4x plus h minus 3 minus y1. I've taken y2 minus y1, x2 minus x1 is a h. I'm just going to do a bit of simplification. I'm going to keep the lim h tends to 0 going. So 4x plus 4h minus 3 minus 4x plus 3 over h. And as we work through this, you'll notice that the x's cancel, the 3's cancel, and you're left with 4h over h, which cancels further to become 4. Okay, so what you're left with, as h tends to infinity, sorry, as h tends to 0, dy dx equals 4. Okay, so as h tends to 0, dy dx equals 4. So I've shown that the derivative of 4x minus 3 using differentiation for first principles gives me a value of 4. So the gradient along that whole line is 4. Right, let's have a look at part B. So part B, I've got x squared, and I've got to show that the derivative of that is 2x. So I'm just going to draw a section of the x squared graph. It's going to help me visualize it. You don't need to draw it all the time. You can just get straight into the formula, but it just helps me visualize the situation. The x value at the bottom one will be x, and the y value will be y equals x squared, so it's x squared. I'm going h along, so a different x value, which is h along. And the y value, if the x value is x plus h, the y value, which was originally x squared, will be x plus h squared. Okay? Now, again, the gradient, dy dx, will be the change in y over change in x. So the change in y is x plus h squared minus x squared over h. Now, I should have included my lim, so lim h tends to 0. Okay, sorry for that. Just going to tidy this up a little bit. I'm going to expand x plus h squared. The expansion's at the top of the page. Okay, so you can use that, or you can just use expansion from your GCSE skills. So expand the brackets there. Okay, and as I think about this, the x's cancel out. Okay, and I can factorize h from the top expression. And cancel out the h, and I'm left with 2x plus h. Now, when we get to this stage, you've got to think, okay, what happens when h becomes 0? What happens as h gets to a limit of 0? Well, as h approaches 0, this value, h, will become 0. Therefore 2x plus h will become 2x. So therefore dy dx is equal to 2x. Okay? So that basically means that along all the points on the x squared graph, the gradient will have the function 2x. Okay, we've shown that by differentiation from first principles. Right, the final question on question 1 looks like this. Okay, so I'll just do it like this. I've got f of x equals x cubed. I need to show the derivative is 3x squared. So again, I'm just going to show a section of the x cubed graph. It does not need to be accurate. One x value will be x and the y value will be x cubed. If I take a different x value, it's going to be x plus h along. Therefore, the y value will be x plus h cubed. Okay. So it's h along. Okay. Again, so the gradient dy dx is equal to the limit as h tends to 0 of f of x plus h minus f of x. So x plus h cubed minus x cubed over h. Okay. Now, x plus h cubed, you need to expand that. Again, the expansion is at the top of the notes. If you expand that carefully, you get this, which cancels out the x cubed. Okay. And let's factorize out the h from the top. So you get 3x squared plus 3xh plus h squared. That will cancel out the h's. And then you're left with just this expression, 3x squared plus 3xh plus h squared. And again, you think to yourself, okay, as this chord reduces in distance from one point to the other, that value of h becomes 0. And as that value of h becomes 0, well then 3x plus h will tend to 0, and h squared will tend to 0. And what you're left with, you're just left with 3x squared. So dy dx is equal to 3x squared. And therefore I have now shown the derivative of x cubed at all points has the function 3x squared. Okay? So that's how you do differentiation first principles in year 12. Okay, there's a set formula, there's a set template. You just got to be able to execute the formula properly and make sure you can adapt it for each function. We'll see in year 13 some more difficult examples where they use trig functions as well. Anyway, question 2 is down here, so we'll final question on the sheet. Use differentiation first principles to find the gradient of the curve 2x squared minus 4x plus 7 when x equals 2. So what we need to do here is find dy dx, find the derivative, and then substitute an x equals 2 to get the gradient. So I'm just going to draw a sketch for the purpose of my own working here. The x value will be just be that. The y value will be 2x squared minus 4x plus 7. If I choose an x value h along, x plus h, the y value will be 2x plus h squared minus 4x plus h plus 7. Okay, and therefore dy dx is equal to the limit as h tends to 0 of f of x plus h, which is 2x plus h squared minus 4x plus h plus 7 minus f of x minus y2. So I'm going to just multiply through this by minus 1 to make life a bit easier. Minus 2x squared plus 4x minus 7 all over changing x, which is h. Right, now what I'm going to do is expand the brackets of x plus h squared and multiply through by 2, so I'm going to do that all in one go because I know what x plus h squared will look like. It's going to be 2x squared plus 4xh plus 2h squared plus 7 minus 2x squared plus 4x minus 7 all over h. Right, what can you cancel out? The 2x squareds can go, the 7s can go, and you can then factorise out the h. So let's just make sure it's correct. So x squared I made a slight mistake here. I forgot to do minus 4x plus h. Minus 4x minus 4h. So I've done the expansion here correctly. I just forgot to do this expansion. So minus 4x minus 4h. So the minus 4x's and the 4x will cancel out. So you've got minus 4h here. So that's minus 4 all over h. See how sometimes mistakes could happen. Cancel out the h's. You're left with 4x plus 2h minus 4. Right, now as h tends to 0, 2h will become 0. And what you're left with dy dx equals 4x minus 4. Okay, which I know using rules of differentiation that's correct, which we'll see in the next video. And I need to find the value of that gradient, so I'm going to sub x equals 2. Which means the value of that gradient is 4 times 2, which is 8 minus 4 there. Right, so let's just recap differentiation first principles. There's a clear structure, there's a clear formula. Okay, a diagram sometimes helps you to reflect on a certain section of a graph. You use that formula, you use some algebra, and you want to try and get to a situation where it will reduce down to a number, either in 1a, an expression, and it's often useful to factorise out h from the top so that it cancels down with the h at the bottom. Okay. And obviously you could get a question where you have to do differentiation first principles and then substitute number in. Okay, so the questions are outlined here, exercise 12b, page 261. I would highly recommend that you have a go at these questions because, as I said, differentiation first principles is a very useful skill and it helps you to understand the rules, which we'll come to later on. Okay, that's the end of the video.